So after having looked at what dimensions are, let's now go on to look at one of the applications of the knowledge of dimensional analysis, and that is checking for the consistency of equations. Now, checking for consistency of equations simply means that whatever is on the left-hand side must be equal or must balance with whatever is on the right-hand side of the equation. Whether it is units on the left-hand side, they must balance with the units on the right-hand side. Likewise, dimensions as well. So, all correct equations should be dimensionally consistent. However, not all dimensionally consistent equations are correct. And for this, we said that in case you look at an example, v is equal to u plus at, this equation is correct and it is dimensionally consistent, as we shall be seeing later on. And if you have another equation like v is equal to 10u plus a half at, still this equation is dimensionally consistent, but it is invalid, it is incorrect. The reason for this is that we have what we call dimensionless quantities. For example, all digits, all numbers, for example, dimensions of 10, for example, dimensions of a half, all these ones, the dimension of any number is always equal to 1, so it is dimensionless. Likewise, we have constants like pi, dimension of pi. This is equal to 1. It is a constant. So, all dimensionless constants have their dimensions as equal to 1. That is why, even here we have a 1, even here we have a 1. So in case you alter these numbers by replacing maybe with the 10, maybe with a half, a fraction, you get the same result as being dimensionally consistent. However, some of them are wrong, like this one here. So that is what I mean by consistency. Whatever is on the left-hand side, be it units or dimensions, they must balance with those on the right-hand side, whether units or dimensions. So that is what we call consistency of equations. Let's look at an example. So for example, in case we have v is equal to u plus at, check and verify whether this equation is dimensionally consistent, where the terms take their usual meaning. Now the v is the final velocity, u is the initial velocity, a is the acceleration, and t is the time. So when you're doing this, we shall simply say that let's begin with the left-hand side. On the left-hand side, we have the velocity v, the final velocity v. So the dimension of the final velocity v is simply equal to L t power negative 1. In other words, remember meters per second, length divided by time, distance divided by time, that is L t power negative 1. Then on the right hand side, we shall simply have dimensions of u plus, this is plus at. When you simplify this, we shall be simply having dimensions of u plus dimensions of a times dimensions of t. The u is the initial velocity, which is L t power negative 1, and then plus dimensions of acceleration, that is L t power negative 2. Remember, meters per second squared. So you have the displacement divided by the time 2 times, or velocity divided by the time, you get this. Then this one times the dimension of the time, which is the capital T. We have a power 1 here. So this is the same as L t power negative 1 plus L t power negative 1. In other words, when you have a power 2 times ay squared, this a here is having 1. So the same as a power 2 plus 1, then times the y power 2. So it's the same as a power 3 y power 2. That's how we deal with indices. We'll be seeing this in mathematics as well. Now, when we reach here, when you have dimensions, this value here, which is the same as this one here, you don't add that this is 1, then you get 2L t power negative 1. No. You simply get the final expression as L t power negative 1 as the answer. In other words, don't get 2L t power negative 1 because this 2 here is dimensionless. Its dimension is a 1. And still remember that in case you have kilograms plus kilograms, you don't get 2 kilograms, you simply get kilograms. So if it is 8 plus 7 kilograms, you get kilograms. So the units don't change. Likewise, even the dimensions also do not change. So we can then come to a conclusion and say that since the dimensions on the left hand side are equal to the dimensions on the right hand side, then the equation is dimensionally consistent. Now, when they're marking your work, they'll be looking at this, the left-hand side, they'll be looking at this on the right-hand side, and of course, you simplify that to this, and then finally, to the conclusion. Take note that the symbol for dimensions must be on the quantity, and once you remove that symbol there, then you simply have the dimensions directly. Otherwise, you can simply use this equation and this. So you simply add this plus this, and then you get your L t power negative 1. But don't use the brackets on these steps here. No. So that is what we call consistency of equations. Let's look at example number 2. So the question is still the same. Prove that the equation above is dimensionally consistent. So what we do again is that we simply separate this into the left-hand side, whereby you have the dimension of the S, and they say that the letters take the Asian meanings, where the S is the displacement, T is the initial velocity, T is the time, A is the acceleration, T is the time as well. So on the left-hand side, dimensions of the displacement S, displacement is length, so we have our capital L. So this is our equation 1 on the left-hand side, it is done. Then on the right-hand side, we shall simply do the same and say that dimensions of ut plus a half, at squared is the same as dimensions of u times dimensions of t, then plus dimensions of a half times dimensions of a times dimension of t squared. So dimensions of u use the velocity meter per second. Okay, so that is L t power negative 1. Then times dimension of the time t, we have the capital T. This is plus, you add dimensions of the a half, that is a fraction, that is a number, it's the same as dimension of 1 over dimension of 2. All those are digits, so everything is 1. Then times dimension of the acceleration, meters per second squared. Okay, so that is capital L t power negative 2. And then times dimension of t squared, which is capital T squared, like that. I said that at this step, you can introduce in these brackets. Here it is, the choice is yours, but don't use these other brackets again. So L power 1, so you have L power 1, then negative 1, t power negative 1 plus t power plus 1, you add the powers, you get 0, so you have t power 0, then plus L times t power 0 again, negative 2 plus 2, we get 0. Any number to power 0, you get 1. So you have L power 1 plus L power 1, which gives us L. Remember, say that don't get 2L, simply because the 2 is a dimensionless constant. So it is having a int of 1. And again, you can't add units and get 2 times, 3 times the unit like that. In other words, meter plus meter, you get 2 meters. No, this is wrong. So don't add the units, still don't add the dimensions. So this is what is on the right-hand side. So you conclude by saying that since the dimensions on the left-hand side is equal to dimensions on the right-hand side, then the equation is dimensionally consistent. Write that in words. And if they're to give you marks, still they look at this step. They look at this step, getting the dimensions up to the final step. Of course, don't change. The dimensions brackets are only written on this step, or any step where you have the quantity. After that, don't use those brackets there. And then finally, the conclusion. So that is our example number 2. Let's look at example number 3 as well. So number 3 says that we have the equation V is equal to the square root of TL over M, where T is the tension, L is the length, and then M is the mass, and then V is the velocity. So prove that the equation is dimensionally consistent. So likewise, we shall simply come and say that the left-hand side, we have the velocity. So dimensions of the velocity, that is known the same as speed, meters per second, that is capital L t power negative 1. That is equation 1 on the left-hand side. Then on the right-hand side, we have to get the dimensions of whatever is there. We have the square root of TL out of the M. So this is the same as square root of dimensions of capital T, which is the tension, times the L, then everything divided by the M. Remember that tension is force. Tension is the same as a force. So they have the same dimensions. And dimensions of the force is the same as dimensions of the mass times dimensions of the acceleration, which is the same as capital M, L, t power negative 2. You can do this on the side, you can bring it in here, it is okay. So this is the same as the square root of dimensions of tension, which is capital M, L T power negative 2, times the dimension of the L, which is capital L, everything divided by the dimension of the mass M, which is capital M. And from this, you can see that this M here cancels out. You end up with L times L, you get L squared, then times T power negative 2. So when you introduce in the square root there, the 2 goes away. So we shall simply end up with L times T power negative 1 as the answer. And this is our right hand side. So therefore, we shall conclude by saying that therefore the left hand side dimensions are equal to the right hand dimensions. And so the equation is dimensionally consistent. Put that in words as well. And that is it. Yes, I had made a small mistake here. This is supposed to be called the square root of dimensions of capital T times the dimensions of L over the dimensions of M. So I had not put this dimension of M here. So please make sure that you put it there. It must be dimensions of M. Then afterwards you can remove them and put whatever is there as shown in the solution. Let's look at the second last example, number 4. Yes, the last example is here, which says that for a streamlined flow of a non-viscous incompressible fluid, the pressure P at any point is related to the height h and the velocity v by the equation. So that is our equation there, where A, B, and D are constants. Rho is the density of the fluid, and g is the acceleration due to gravity. Given that the equation is dimensionally consistent, find the dimensions of A, B, and D, and hence their units. You can pause the video and try it out first. Okay, hoping that you've tried it out, let's try to do it together. Now, when you're adding, let me begin by relation here, that if I have 2 kilograms plus 8 centimeters, what answer do you get? Of course, yes, this is impossible. You cannot add goats to cows and so that you have this number of goats or you have this number of cows. No, they are inseparable. Simply end up by saying that you have this number of cows and this number of goats. Likewise, you cannot add a kilogram to a centimeter. These two units are totally different. They're units of different quantities. Now, in the same way, it means that when you're dealing with dimensions of physical quantities, when you're adding or subtracting quantities, you must be adding or subtracting the same quantities. Centimeters with centimeters, meters with meters, kilograms with kilograms, and so on. Which means, therefore, that whatever you have in brackets whereby you're going to be adding or subtracting, those two quantities, for example, for the P and the A, they have the same units. The H and the B are having the same units. The V and the D are having the same units. So which means that our work is going to be very simple. So you'll simply say that since you're adding or subtracting, then it means that for P and A, they must be having the same units. And same units means same dimensions. Therefore, you simply conclude that by saying that dimensions of A are the same as the dimensions of P. And what is P equal to? P is the pressure. Pressure is equal to force out of the area. So meaning that the dimensions of P is the same as the dimensions of force over the dimensions of area. Do you remember the dimensions of force? If you don't remember, use the equation. Force is the same as mass times the acceleration over the dimensions of area. So mass is capital M, acceleration is L, T power negative 2 meters per second squared, remember. Then over area, it is L squared. This is the same as M. We have a 1 here. When this one goes up to be 1 minus 2, you get L power negative 1, then T power negative 2. So we'll simply bring that one here and say that this is the same as capital M, L power negative 1, T power negative 2. And that is the dimension of A. And hence, unit of A will be, M is the kilogram because it's mass, so you have kilogram. L is the length, so you have per meter. And then T is the second, so you have per second squared. And that is the unit of this. In case you remember that P is pressure, then you can simply come and say that this is the same as PA, pascals. But you want everything expressed in terms of the mass, length, and time. So express that in the base units. So that is A. How about B? So for B, we are still subtracting or adding, meaning that H and B have the same units. So if they have the same units, it means the dimensions of B is equal to the dimensions of H. And the dimension of H, they say that H is the height. H is the height, and that is length. That means that is capital L. And hence the unit of B is a meter. The SI base unit of B is a meter, and that is all. Lastly, the D is here. So since we're subtracting all, adding, the V squared and the D must be having the same units, meaning therefore that the dimensions of D are the same as the dimensions of V squared. And this is the same as the dimensions of V outside brackets like that. What is the V? V is the velocity. So you simply have this one as LT power negative 1 into brackets squared. So this is the same as L squared T power negative 2 squared. And hence the units of D are meter squared per second squared. That is the unit, the SI base unit of D. So with this, I come to the conclusion of checking for the consistency of equations. And coming up next is a quiz for you.